Look up at a clear night sky, and you are immediately confronted by the sheer scale of the cosmos. Our galaxy alone contains hundreds of billions of stars, scattered across a vast expanse of nearly empty space. But when you isolate just one of those points of light, the immensity of the universe becomes a stark, practical problem. Earth scientists can physically sample rocks, measure fault lines, or drill into ice cores. Astrophysicists cannot. Our subjects are separated from us by trillions of miles. We can never reach out and touch them. Compounding this distance is our own atmosphere. The distorting effect of the air above us blurs stellar images over an angle of about 1 arcsecond. Even with powerful ground-based telescopes, stars remain unresolved. They are nothing more than dimensionless points of light. Because we are dealing with points, we are restricted to exactly 3 raw observables. The first is the star's precise coordinates on the 2-dimensional celestial sphere. The second is its apparent brightness, the raw energy or flux of the light that actually survives the journey to strike the mirrors of our telescopes. And the third is the star's color spectrum, obtained by splitting that incoming light into its constituent wavelengths. That is the entire raw dataset. The discipline of stellar astrophysics is an act of mathematical translation. By pushing position, flux, and color through a strict geometric and physical pipeline, we reverse engineer the absolute 3-dimensional reality of the star, its true distance, its absolute power output, its surface heat, and its physical diameter. The pipeline begins with the most immediate problem, determining depth in space when you have no physical measuring stick. The solution is trigonometric parallax. By shifting our own perspective, we can observe how an object appears to move against a static background. We cannot walk across the solar system to change our perspective, but the Earth does it for us. By waiting 6 months, Earth's orbit provides a built-in observational baseline of 2 astronomical units, about 300 million kilometers. Viewing a nearby star from opposite sides of the Sun creates a measurable parallax angle, P. The geometry simplifies into a direct relationship. Distance equals 1 divided by parallax angle. This gives us the parsec, the distance where this angle is exactly 1 arcsecond. Establishing this physical distance is mandatory for the pipeline. Without an absolute geometric anchor, the rest of the physical equations in the astrophysics pipeline remain mathematically unsolvable. With distance locked in, we can move to the second raw observable, apparent brightness. Astronomers measure this as flux. Flux is the raw energy per unit area, per unit time, that hits our detectors here on Earth. The limitation of flux is its ambiguity. A bright point could be a small, dim star right next door, or a massively powerful star thousands of light years away. As light travels outward, its energy is distributed over an ever-expanding sphere, dropping in concentration with the square of the distance. Because distance is known, we algebraically rearrange the equation. Multiplying observed flux by the spherical area definitively solves for absolute luminosity. Because the variations in stellar power are so extreme, astronomers categorize these values using a logarithmic magnitude system known as the distance modulus. Calculating intrinsic luminosity removes the optical illusion created by vast distances. It proves that what appears as a faint speck is actually a nuclear furnace, emitting millions of times more power than our own sun. The pipeline now turns to the third and final raw observable, color. The light a star emits is thermal radiation. It is generated by the violent, high-speed collisions of atoms reacting to extreme heat within the star. The distribution of this emitted light is strictly dictated by the object's temperature. The heat causes the star to output energy across different wavelengths in a highly predictable curve. The Planck blackbody spectral energy distribution plots emitted energy against electromagnetic wavelengths. As thermal energy increases, overall power jumps, and the entire curve shifts left toward shorter, higher energy wavelengths. By locating the absolute peak of this curve, Wien's displacement law states the star's temperature is inversely proportional to its peak wavelength. By simply observing which color of light the star emits the most of, we use this formula to extract a precise numerical value for the heat at the star's surface. Measuring color transforms our telescopes into interstellar thermometers. we can accurately read the surface heat of a star thousands of light years away without ever leaving Earth. At this stage in the pipeline, we have acquired two massive pieces of physical intelligence: the star's total power output and its surface temperature. Yet, in our telescope lenses, the star remains exactly what it was when we started: a dimensionless, unresolved point. To deduce physical size, the Stefan-Boltzmann law connects known luminosity and surface temperature. Total emitted power is the thermal flux of 1 square meter, multiplied by the spherical surface area, 4 pi r squared. We algebraically rearrange this to isolate the unknown variable, r. We have just deduced the exact physical diameter of a sphere we cannot actually see. Through pure logic, a dot on a telescope sensor becomes a massive physical object with a defined scale. There is one final layer of data hidden in the light arriving from that point. A star is not uniform. It consists of a dense, incredibly hot interior that emits a continuous, unbroken spectrum of light. But surrounding this core is an atmosphere of cooler, lower-density gas. As the continuous light travels outward from the core, it passes through this cooler atmosphere. The atoms suspended there intercept the light, absorbing specific photon energies that match their internal quantum transitions. This image reveals the result. When we look closely at a stellar spectrum, we find it is interrupted by a complex sequence of distinct dark gaps known as Fraunhofer lines. The energy at these precise wavelengths has been absorbed. Because different elements possess unique orbital structures, the exact wavelengths of these dark lines act as an atomic barcode. They positively identify specific elements, like hydrogen, helium, and carbon, in the star's upper atmosphere. But the strength of these absorption lines is entirely governed by the gas's ionization state. If a star is too hot, electrons are stripped away. If it is too cold, they lack the energy to jump. This dynamic gives us the OBAF-GKM spectral classification system. As this chart shows, stars of different temperatures exhibit completely different absorption line profiles. Reading these absorption lines provides a detailed chemical assay of the star's composition. More importantly, it acts as a secondary, highly rigorous confirmation of the surface temperature we calculated earlier. What begins as a single trembling point of light in a telescope has been systematically unpacked. By capturing just a few two-dimensional variables, we have constructed a complete three-dimensional physical profile of a star. The sequence is mandatory. Position data yields trigonometric distance. Distance allows us to determine true luminosity. The color curve isolates the surface temperature, and integrating luminosity with temperature physically measures the radius. This analytical pipeline is the foundational toolkit of modern astrophysics. Extracting these baseline parameters is not the end of the work, it is merely the required starting point. Knowing a star's true mass, radius, and temperature provides the initial conditions we need to model its internal nuclear fusion. It allows us to chart the billions of years of stellar evolution and accurately predict exactly how and when the stars will eventually die.